Okay, we're on the last question on the related rates note. In number 5, it says the radius of a melting snowball is decreasing at a rate of 2 centimeters per hour. Determine the rate at which the volume of snow is decreasing when the radius is 10 centimeters. So again, we always want to draw a bit of a diagram. We know that a snowball would be a spherical shape. And we can define our variables. So here we're going to have our radius and our volume. And each of these is going to be changing in terms of time. So for instance, we will have a rate of change or the derivative of the radius function in terms of time and a rate of change in terms of time of the volume function. So again, kind of reading through, thinking about what you know. It says the radius is decreasing at a rate of 2 centimeters per hour. So that's really important to make sure you get the right sign in here. So dr dt would be negative 2 centimeters per hour. And it says when the radius is 10 centimeters. So we are looking at the rate at which the volume of snow is decreasing. So the rate of change of the volume, that's what we want to be able to find. So you can put in a question mark there. Now we don't know the volume, but in one of the earlier examples we found, I think it was for area of a circle with the water dripping, we found the area and we could find the volume here, right? If we know the radius of a snowball, we could obviously just use the formula to find the volume. And if you guys don't remember the formula, which I don't really expect you to, the volume there is 4/3 pi r cubed. So we could sub in a 10 here and figure out the volume, but I want you to kind of pay attention and like look ahead a little bit. When we do the derivative of the left side here, we're going to do the derivative of v, which is 1 times the derivative of the volume function. So that's dv dt. So here we don't actually have a volume variable left at all. So we don't need to go find the volume. We absolutely could. And if you just kind of get in the habit of finding it all right away, that works really just fine as well. And then on the right hand side here, we're going to do the derivative of 4/3 pi r cubed. So remember, pi is not a variable, it's part of this coefficient here. So I'm really doing the derivative of r cubed, which is 3r squared. When we multiply this coefficient by 3, it will reduce with the 3 on the bottom. So we get 4 pi r squared. And then we have to multiply that by the derivative of the function. So this is dr dt. And now again, we just substitute in all the numbers we know and solve for dv dt, not even any real rearranging or anything. 4 pi times 10 squared times -2. So that's -800 pi centimeters cubed per hour. Make sure you're careful with your units there. We were measuring centimeters per hour from the radius, so the volume would be centimeters cubed per hour. So we could write a therefore statement. Therefore, the snow is melting, or the volume of snow is decreasing at a rate of 800 pi centimeters cubed per hour. And we could multiply in that pi for sure. Notice here, if I'm saying decreasing, I don't also need to include the negative sign. That's a little bit redundant, but we know that that negative means that the rate of change is negative, so the volume is decreasing.